Okay, so hello everyone. I'm very sorry not, and yes, I had some teaching and family question that made the mobility a bit difficult. But I will change a bit radically the topic, I think, and discuss a bit this sustainability question and start where do we come from? I would say a few centuries ago we were, at least in Switzerland, comfortable in our mountains hut, sustainable local materials. The beautiful mountain huts that I was showing initially, this Swiss and we compare the straight wall and a complex wall, and we show that effectively this like double curved wall, you had effectively an increase in productivity when you were dealing with such complex shape, which you didn't have if you were not dealing with complex shape. You have exactly the same result for environmental impact. It means that you have an environmental benefit of building through digital fabrication if you're dealing with complex shape. So to summarize, you could say, okay, innovation, technology, and technological revolution, they are needed to avoid the collapse of our socio-technical systems. Digital fabrication as such effectively can be characterized as a revolution because it can handle a higher level of complexity without additional cost and somehow is therefore needed. And now comes my question on sustainability, that maybe the bigger threat to our society might not be to collapse from internal complexity. It is just to collapse because the natural system that is supporting us is actually collapsing. And that's what we observe with climate collapse and biodiversity collapse and etc. So let's reframe the question and say, okay, maybe can digital fabrication, by avoiding the collapse of our socio-technical systems, also avoid the collapse of natural systems? And so then the question is, can the extra complexity available through digital fabrication be useful for sustainability? And I would like to show a few work that have been done, a literature survey done by Marcel Assad and others, who kind of compared digital fabrication or additive manufacturing here and conventional construction, and they show, yes, in general, it is better, but not always, typically. And why? Is just because you have relatively, sorry for simplifying the question, but you have very simple drivers. You have an impact of material production, you have a certain amount of material that you use, and you have an impact of the production process. So the only question that you have is that the impact linked with the additive manufacturing should be lower than the one that is conventional. Usually what you have is that the impact of the material for additive manufacturing is slightly higher than conventional because you reduce the size of grain, because I mean, for a few aspects, and the impact of the process is also higher because you have a robot. So the question is how much volume you need to reduce in order to compensate this increase of impact. And so that you need to save materials. You have two solutions. The first is to save material through, let's say, structural optimization. Here you have the ripped, stiffened funicular flow systems developed by Borg Research Group, where you reduce a lot the volume of the concrete. And you see here that the digital fabrication product is much lower in terms of impact than the conventional one, although the concrete per cubic meter is much higher because you have reduced it, you have more cement per cubic meter, but you use so much less material that you're still better. And the question here is, what is the impact of the production process? Because that's, again, to take the work of Marcela, if you compare the additive manufacturing technique and the conventional technique and look at the contribution of the material and the process, you see that especially for 3D printing, not necessarily robotic additive, but 3D printing, you have an impact of the construction process that is much more important than conventional construction. It could achieve 50% of the total impact. So it means that your structural optimization first needs to compensate the impact of the additional materials the additional impact from the materials, but you also need to compensate the additional impact from the construction process. And there, it means you need to save a lot. That's a study, data adapted from a study from Katarina Kuzmenko and co-authors, and they kind of showed this. It's like, for processes where you don't have an intensive process, like robotic assembly, for instance, your volume saving should be around 40–50%. So you need to save 40–50% compared to conventional construction to start to be more climate friendly. For processes which are process intensive, then it's a different. That's the blue one. It's different. If you have a material that has a high impact, then the process contribution is small, and so you're around in the same range. But if the material has a very small impact, then the contribution of the process is quite high, and you need to save a lot of material to compensate the process, which then can reach kind of 80% compared to conventional process. So that starts to be that's difficult, I would say. The other way of saving material, which is a radically different way of doing, is to what I would call functional hybridization, is to think, and I take the example of this robotic assembly timber roof from ETH that is built by Gramazio and Kohler. It's a structure. It's a structure, but it is also a suspended ceiling. It has acoustic performance, thermal performance, and finishing performance, I would say. And then we compare a conventional roof and a sequential, the sequential roof, and you see that the structure, you don't have saving. It means you usually have used as much material as a normal timber frame structure where you have a roof with timber beams. But what you have avoided is the suspended ceiling that you would use normally. So you have an additional function, and this makes your saving. And you make your saving through the specific shape that is providing through digital fabrication. So that's this aspect. Difficulty with that is that it goes against the traditional sustainable principle guidelines of sustainable design, which usually say you have to separate the different function, because the skin, the structure, the services, the staff, etc., don't have the same service life. And when you start to do functional hybridization, well, it means the structure and the technical systems will be embedded in the same element. What is the service life of this element? If you compare this, because it's in wood, even with an uncertainty on the service life, if it's a ceiling or if it's a structure, it doesn't make that much difference. But if it starts to be a concrete, like where you have optimized the structure, you have saved material, and then you try to put technical systems inside. Does your final concrete structure act as a structure, and so will have a service life of 60 years, or act as a technical systems, and so will have to be replaced every 20 years? And then it makes the difference. So to summarize, complex shape can be produced with no additional cost with digital fabrication compared to conventional practice. And as such, I think it allows to handle an extra level of complexity, which increases the productivity and is probably needed to avoid the collapse of our society. In order to additionally support the natural systems our society relies on and be considered as a sustainable technology, you need to use this extra complexity either to structurally optimize your element or to embed multiple functions within one element. And of course, embedding the multiple function need to be think in terms of the fact that they don't necessarily have the same service life. So how do you deal with the adaptability of the future use? And finally, for certain techniques such as 3D printing, the impact of fabrication process is not negligible and requires then even more saving on the material volume than the initial just structural optimization. And with that, I would like to thank you, and I'm sorry for the problem, technical.
Hello, Guillaume. Nice to meet you. Any questions for Guillaume? Yes, around there. The usual suspect. What's wrong with you?
I don't know.
You got me running back and forth.
Hello. This talk was really interesting if you work in 3D printing, because it's a lot of questions I ask myself every day. And I have two things I wanted to ask you if you put this into account as well. Because we mostly have very complex problems. And I noticed that complex problems most of the time take just longer to plan. And I was wondering if this longer planning period can also be considered like less sustainable, because basically more people have to go to work more often and consume more energy to actually be able to plan. This is the first thing. And the second thing is, if in these digital processes, you most of the time have to touch every point of a structure, which requires energy again. And this touching every point of the structure again is a very energy intensive process that most of the time gets canceled out of the calculations. So I was wondering, what are your thoughts about this, or if you put this somehow inside your thinking?
Yes, thank you very much. I'm not sure I got exactly your touching of the points of the structure. What do you mean, that you have to calibrate all the time, or? No. So maybe I first answer to what I understood. The planning process, for sure, you could say that with a digital process, you could potentially save or shorten the planning and the interaction. Usually, we don't consider this as in the environmental impact. Especially because you would say these people, to be very brutal, but you would say these people they leave, they work, and so if they are not doing this, they would be something else. So it's not so much an increase of an environmental impact because you're doing planning or you're not doing planning. I mean, let's say the activity of the people, you don't integrate that in the environmental impact. What you consider is the energy that you consume, so the electricity, etc., and the material. What the only interest I would say in the planning, which I could see as an interest, is that we are approaching the let's say the cliff of a climate collapse as extremely fast, and effectively these projects, they usually take a lot of time to plan. So the project that we are planning now, they will be implemented in 7-8 years, and to have a shorter planning phase allow probably to be more aligned between what you can produce in terms of material or planning and what you can implement, and avoid to have a somehow nearly outdated technology at the moment of the building is constructed. So if we really need to reduce by 50% of emission in 5 years or in 10 years, you better have a short planning period, even for complex projects. So this is potentially where I would see an interest, is that you have a higher flexibility and you're better adapting to an extremely fast reduction of emission that we, in terms of constraints, that we will have. So that's where I see, but the second aspect of the question, I have to say that I didn't completely get it. I'm sorry.
Now? Okay.
Yes,
so
now I hear you. Yeah.
I don't know, it's a bit tough to explain, but if you, especially with extrusion-based processes, you basically have to imagine you slice your part in layers, and then you have to touch every virtual point of your curve that creates the layer, that creates the part. That's like a lot of movement, like there's so much energy to create this thing. While if you would, for example, make a mold and pour it in a not so complex shape, then you wouldn't have all of this energy. And this is never calculated somehow in all of these things, I feel, because we have quite a big electric bill when we do these things. Yeah.
No, effectively, I think yes. So now I understand, and I think it's exactly what the work of Marcella Saad tried to show, is that but I was fast. But if you look at the global warming potential in terms of the contribution of the total impact from the material contribution, so typically the embodied emission, and the process, which is a little bit what you say, the fact that the robot needs to go all the way through all the curves and the contribution of the process is actually much higher. So usually in conventional construction, you would say 20% on average comes from the process and 80% comes from the average from the material. In digital fabrication is it's kind of the opposite. The 20, I mean, especially for 3D printing, 20% come from the material, 80% comes from the process. So and this is due for this is the combination of two aspects. You use less material, so of course the contribution of the material is reduced because you have saved material. That's one point. The second point is effectively the energy that you put in the robot is much higher than if you just pour the material in a formwork, and so that's why in terms of saving of material, you need to save both the extra impact of, I mean, you need to save material to counterbalance the fact that effectively you have impact on the process, which is then which has been quantified by Katarina Kuzmenko, and which is what I showed here, and they have done kind of a really good calculation on the environmental impact linked with the robotic arm. which is what I showed, is like if you have low carbon materials, the contribution of your electricity bill, basically, it's all it is all the impact that you have, and so you need, if you want to compensate that, you need to save a lot of material or a lot of volume compared to a conventional process. Yes, and maybe to continue on that, it is a little bit the same question as the electric car, is that you're consuming electricity, the environmental impact comes from what type of electricity has been produced. And so if we are, let's say in Switzerland, you have nuclear power electricity, then the carbon footprint is lower. If you're in another country where it's mainly coal-based, then the carbon footprint of your robot is actually, of your process is actually much higher.
Thank you very much, Guillaume.